Hi everybody, this is Mr. Yeoman, and today what we're going to be talking about are isotopes. Those isotopes are just atoms of the same element, but they have different mass numbers. So I know that as we've been going over the history of the timeline, we haven't talked about all of the pieces yet, but we're going to start pulling those pieces in. So we have discussed the electrons, we have discussed protons. Rutherford hasn't quite figured out what protons are, but he knows that there's a positive in there. And so we know that atoms are made up of a number of protons. That gives them their function, how they behave. Okay, so every element has a symbol that goes along with them. So they have a letter that denotes what type of atom it is. In this case, it's a letter C, which is for carbon. And this is telling us that we have a mass number of 12, as well as an atomic number of 6. So again, Rutherford hasn't figured everything out yet, but eventually they're going to get to the point where they know that the numbers on the periodic table, so carbon being element number 6, means that it has 6 protons, and its total mass is a mass of 12. So what that's going to end up looking like, this is carbon 12, is if we look at the nucleus of a carbon 12 atom, it's going to be made up of protons and neutrons. Again, we don't know about neutrons yet based on the timeline of atomic theory. However, this proton and neutron, we know that there's going to be 6 protons because it is carbon. Okay, we know there's going to be 6 electrons because Thomson told us that atoms are neutral. So if there's 6 protons, there have to be 6 electrons. And so the last thing that we don't know about yet, but we will shortly, is the neutrons. So if this is carbon 12, it has a total mass of 12. 6 of those mass units are coming from the proton, so that means the other 6 have to come from neutrons. Okay, so if we compare that to this other carbon atom right over here, the nucleus looks a little bit different, but it is also made up of protons and neutrons. But this is instead carbon 14 rather than carbon 12. So it is carbon, meaning that it has 6 protons. Because we have 6 protons, that means we have 6 electrons because it is neutral. But that means that we have to have 8 neutrons in order to make our total mass of 14. So looking at some of these other elements, again, we know that there are 3 protons, and so then there are a total of 3 electrons here. So this looks very much like the Rutherford planetary model. But this one is a little bit different. It has 3 neutrons versus 4 neutrons. They both have the same number of protons. They both have the same number of electrons. The only thing that makes isotopes different from one another are the number of neutrons. Otherwise, they act in just the same way as every other element of its type. Okay, so this first one is lithium-6. It has a total mass of 6. We know that it's lithium because it has 3 protons. So if we go to the periodic table, find element number 3, that is lithium. Same thing over here. It's still 3 protons, so we know that it's lithium. However, this time the total mass is 7. So these are just isotopes of one another. Again, the nucleus is different, but this has 3 protons, and then we can see the 3 neutrons, a little bit smaller nucleus than carbon. And the alternative version is still the same thing. We have 1, 2, 3 protons, but now we have 1, 2, 3, 4 neutrons, making this lithium-7. Okay, it's pretty straightforward. We're going to be getting into some things regarding ions as well, which will change it a little bit. So let's try one out here. If we take a look at chlorine, this is chlorine 37. Usually chlorine has a mass of about 35. But this is just a type of chlorine. So it has this little number up here in the corner. So that's chlorine 37, and so the 17 is telling us that it has 17 protons. Okay, look at this. The 37 is telling us that's the total mass of the protons and neutrons. So if we have 17 protons, then that is going to tell us that we have 17 electrons and 20 neutrons. Okay, pretty straightforward. At this point, we're not going to, the electrons are always going to be the same as the protons. That'll change when we get a little bit further down the road when we talk about ions. But right now, as far as isotopes are concerned, we're only looking at the number of neutrons that are changing. Okay, so the reason that these have certain masses is because the parts of the atom have different masses. We use something called AMU, that stands for atomic mass unit, because this is so tiny. We can give it a mass, like we can measure it in grams, but it's going to be so small, it's not really meaningful. So 1 AMU is 1/12 the mass of a carbon atom. So looking at that, that means that there are 12 pieces to a carbon atom, and so we're assuming that each piece is the same size. Now, that's a little bit of a lie because they are a little bit different. If you take a look at this, one proton has a mass of 1.007276 AMU. But really, that's pretty close to 1. It's 1 AMU. That's what we generally consider it. Neutrons are also slightly bigger than protons, so 1.008665 AMU. But again, they're almost the exact same size. So we pretty much always consider that. Now, if you look at an electron, it's not the same. It is super tiny. It's not even close to 1. It is almost 0. If you, depending on where you round this, it is 0. So we have two particles, the proton and the neutron, that are almost the same size. And then we have the electron that is super tiny. It's not even going to count when we are considering that into the mass of the atom, which is why we don't figure it into our carbon-12. We're only figuring the neutrons and the protons because the electrons really don't have that much of a mass. All right, so that's where we're going to stop for today. Hopefully you can go over this and this makes sense. We're going to do some practice here on Friday and hopefully make this a little bit more solid about what an isotope is and how isotopes became important for the Manhattan Project. Have a great night, and I will see you tomorrow.